All right, so we're going to do the notes for 7.4. We've got 7.4, 5, and I think 6 is all we have to do. So we're going to talk about a lot more trig identities. And we've had some trig identities so far. The big one we have had is the Pythagorean identity, which is sine squared theta plus cosine squared theta is equal to 1. And we know that there are other forms of that identity that we're going to look at again. So I think we're going to skip this exploration. The exploration talks about the fact that let's show that this is true using your calculator. So you would, for example, plug in to your calculator, you would do the sine of 35 degrees and you would square it plus the cosine of 35 degrees and you would square that and you would show that it is equal to 1. So hopefully you'll just trust me and know that yes, it does equal to 1. Okay, and same thing with 5 pi thirds. If you put your calculator in radian mode and did that one, you're going to get equal 1. So that is a true identity. In fact, it's the granddaddy of them all. Okay. So let's go down and let's talk about what makes an identity different from an equation. Okay, because we're going to be showing that identities are true for the rest of the course. So an equation that is not an identity is called a conditional equation. These are conditional equations. 2x minus 6 equals 5 is a conditional equation. It is only true if x is equal to 11 over 2. Sine x equals 0 is a conditional equation because it's only true if x is an integer multiple of pi. So it's true if x is 0 or pi or 2 pi or 3 pi or 4 pi. Those are conditional equations, okay? Two functions, f and g, are said to be identically equal if f of x is equal to g of x for every value of x for which both functions are defined. So conditional equations are only true for under certain conditions, under certain x's, whereas two functions are equal if for every x, f and g mean the same thing. So for every x for which both functions are defined, such an equation is referred to as an identity. And an equation that is not an identity, we just talked about, is called a conditional equation. So we've been solving conditional equations, through our whole math career, and we actually did them when we did trig equations because those trig equations were only true. We found specific x's that would make the equation true. Now we're going to be working with identities, so it's going to be slightly different. So before we go ahead and look at the identities, and solve or prove identities, let's go ahead and let's review our identities that we have so far. So the basic trig identities, we know that the quotient identities, tangent theta equals sine theta over cosine theta. We know cotangent theta is equal to cosine theta over sine theta. So this will be a nice piece of paper that you can have with you. Reciprocal identities, we know cosecant theta is 1 over sine theta. Secant theta is 1 over cosine theta. And cotangent theta is 1 over tangent theta. So those are called the reciprocal identities. The Pythagorean identities, we've looked at these. So the big one is sine squared theta plus cosine squared theta equals 1. And remember, I showed you in another set of notes how to get the other two. So for example, if I were to take this identity and if I were to divide everything by cosine squared theta, I would end up with this identity. So if I divide this all by cosine squared theta, that means I would get 1 over cosine, which is secant squared theta. And then if I were to take this and divide it by sine squared theta, I would end up with this identity, which would give me cosecant squared theta. Now, I also want to just quickly write down, and especially for this one, there are other forms that you will often use this identity for. So for example, if I were to solve this identity for sine squared theta, it would look like sine squared theta equals 1 minus cosine squared theta. You use that a lot. And if I would do the same thing, except this time solve it for cosine squared theta, I would get cosine squared theta equals 1 minus sine squared theta. We use that a lot. So I just wanted to write those in there for you, just to show you. We've talked about even versus odd. So remember, the only even trig functions are cosine and secant. So remember what that means if we fill these in first. It means the cosine of negative theta is the same thing as the cosine of theta. Same thing with secant of negative theta is the same thing as secant theta, whereas with sine and tangent, those are odd functions. So the sine of negative theta is actually the negative sine of theta. And same thing for cosecant theta. Same thing over here for tangent. The tangent of negative theta is negative tangent of theta, and cotangent would be the negative cotangent of theta. Okay, so we're going to go through some proofs, quite a few of them, and we're going to talk about some strategies that you can use when you're faced with a proof to do. Okay, so here we go. Our first example. So one thing you can do is to, so one method of simplifying trigonometric expressions is to multiply by a well-chosen one. So here's what they mean. I can simplify sine theta over 1 minus cosine, or 1 plus cosine theta by doing the following. I'm going to multiply top and bottom of the fraction by the same trig expression, which is totally legal as long as you multiply top and bottom by that same expression. And the expression that I am going to choose is 1 minus cosine theta. Now, let's see why I chose that one. So remember, it has to be a well-chosen. If I multiply out the denominators, if I were to FOIL these two trig expressions out, I would get 1 minus cosine squared theta. If I multiply out the top, well, I'm actually not going to multiply it out, but I'm going to write it over the same denominator. So now, why was that such a good one to choose? Well, if I look at the bottom, that is actually equal to sine squared theta. Look at that previous page that I showed you. So this is equal to sine squared theta. Why does that help me? Because I can cancel that sine theta with one of these, and I'm left with 1 minus cosine theta over sine theta. So I don't know if I'd really call it simplifying. These two are equivalent. They mean the same thing. I don't think really one is more simple than the other, except for maybe this one had a binomial on the bottom and we've moved it to the top. But that is a strategy that you often use, multiplying top and bottom of the same of the fraction by the same trig expression. And usually it will be the conjugate. Notice how it's the conjugate, because when you multiply conjugates, then the middle term will disappear. Okay, so another thing that you might want to do is you might want to add two fractions or subtract two fractions. And of course, to do that, you have to put it over a common denominator. So here's a quick review of doing that. So if I want to simplify 1 over 1 minus sine theta plus 1 over 1 plus sine theta, I'm going to combine them. My common denominator would be 1 minus sine theta times 1 plus sine theta. So if I go down and if I look at this expression, I'm simplifying this. So here's the first fraction. So if I want to get it over the common denominator, I'm going to multiply top and bottom by 1 plus sine theta. And here's the second fraction. To get that over the common denominator, I'm going to multiply top and bottom by 1 minus sine theta. So let's see what that gives me on the top. Well, 1 plus sine theta times 1 is simply going to be 1 plus sine theta plus the numerator over here will be 1 minus sine theta. And again, each of the denominators, when I multiply those out, will be 1 minus sine squared theta. If I multiply them out, let's see if I actually add the numerators, the sine thetas will drop out, and I end up with 1 plus 1, which is 2 over, and if I take the 1 minus sine squared theta, what is that actually? Well, that's cosine squared theta. And if I want to simplify 2 over cosine squared theta, remembering that this is really 2 over 1 times 1 over cosine squared theta. And what do we know 1 over cosine squared theta is? That's the same as secant squared theta. So this becomes 2 secant squared theta. And we've simplified it. So there's another strategy. Again, just go ahead and combine the fractions, but you're going to have to find a common denominator. Now this is a lot of paper for one example, so I realized that, but the next one took the whole page, so I was stuck with it. So another strategy that you're going to want to do is factor something that can be factored. So for example, if we're looking to simplify this trig expression, you'll notice that I can do some factoring on both the top and the bottom. The top is a difference of squares. So that would be 1 plus cosine v times 1 minus cosine v. The bottom, I can factor that by taking out a sine v as a common factor, which would give me 1 plus cosine v. You can see that the 1 plus cosine v's are going to cancel. So I end up with 1 minus cosine v on the top over sine v. And I'm not sure what that equal sign is there for, but we don't need it. We have simplified this trig expression to look like this. So again, we're not actually proving identities right now. We're just going through and we are learning some strategies that we might have to use. All right, I think we're going to do one more and then we'll change the video. Let me just quick check. Oh, actually, I think I'll switch videos now.